Hi guys, sorry, I think possibly we were unmuted there, so hopefully you can hear me now. It was just the introduction slide and then a disclaimer, and now we're moving on to brocaded Ethernet fabric. By the way, if you have any questions, I think you can either use the online texting facility, or we'll take questions at the end. So yeah, back to Ethernet fabric background. I'm going to presume that guys on the line have at least some background already in Ethernet fabric, so we'll sort of breeze through that and highlight some areas of the technology which are relevant to storage and NAS, and then we will move on to more specific areas like DCB lossless Ethernet and how that's very applicable. But let's have a look through fabric itself. Right. Sorry guys, just trying to get the slides to advance. Right, so brocaded Ethernet fabric products have been shipping, as you can see here, for over 2 years. I expect you're familiar with the tranches of hardware that we've released and the tranches of network operating system that we've released and all the additional features that have come in along the way there. And you can also see the number of customers increasing along the bottom of the graphic there. So, you know, right from early days of fixed format products with the 6720, moving through to 6730 products with native fiber channel and 6710s with 1 gig connectivity, and over on the right hand side, which I hope you can see because it's obscured on my slides, but the 8770 chassis product with, of course, very high density of 10 gig and 40 gig. And of course, yeah, releases of NOS along the way there as well. So moving along quickly to trill, I think you're probably all aware, if you know the background of Ethernet fabrics, that transparent interconnect lots of links, an inspired name I always think, but it's, you know, it's one of the key technical enablers for the fabric technology. So developed, you know, by the IETF, including by Radio Perlman here. So a slide on a bit of history there, including the poem that she wrote actually when she originally penned the standard for spanning tree. If you guys are old industry guys like me, you probably know some of the history here, and the fact that really spanning tree wasn't designed for larger scaled layer 2 domains, as we've seen them increasingly used or tried to be used, and we've probably all spent late nights in data centers or campuses trying to debug what was going on spanning tree. So, you know, not really designed for large fabrics or you know, multiple open link states. So what trill gives us here is the ability to have all paths open across the fabric. So instead of, you know, adding up costs from root bridge and then blocking links somewhere in the infrastructure, but only having one path open, we have all paths open. So again, as I say, you probably know some of the history to this, and the fact that trill is really using a shortest path first algorithm, techniques usually used in the routing world at layer 3, but here we're using that algorithm to understand all the paths across the fabric. So, you know, we're really advertising MAC addresses across the fabric rather than network reachability at layer 3, but using the same shortest path first techniques. And kind of what this means is that all the paths, they're still at layer 2, but they're all available and all able to carry data. And we can then use techniques like equal cost multipath to share data across multiple links in a low balancing fashion. Some history there, like you probably know that ISIS is mentioned in the RFC standard there, but, you know, thinking back to the graph that I had before, this kind of early entry into the market and this good sort of 2-year gain that we have on other vendors in here was probably instigated by our idea of using our FSPF, fiber shortest path first, from our fiber channel products to satisfy, you know, the requirement in the RFC that a shortest path first algorithm be used. So moving on, I'll build this one quickly. I hope the PC will build here, but you know, really repeating what I've said already there, that you know, all paths are active and all are load sharing across the network. As I say, I'll skip through these because I'm assuming that you've seen some of these advantages before. It's probably a reminder, and if you haven't, then hopefully at least it gives you some sort of background to what goes on. So a quick point about this ECMP equal cost multiplier path selection across our fabric. A little bit more background on how we get extremely good load balancing across those multiple links that are available, and also in the next slide a little bit about load balancing on the individual inter-switch links between each device that you see there. So you can see they're labeled VDXs. There could be actually any one of the products that you saw on the graphs. They're all just nodes or R-bridge ID. So the trill, standard main dates, and R-bridge ID. You just need a unique number and ID for each one of those devices. So there could be any mixture of, you know, 6720s, 30s, even 8770 chassis. It's just a node within the trill Ethernet fabric. So yeah, let's look at what happens at ECMP. So first of all, if you see on the graph there, on the slide that is, you see we have twice as many 10 gig links in the kind of northbound direction where I've got IP flows left, so we have IP flows right to the bottom. We've got 4 10 gigs at the top and 2 at the bottom. So, you know, at ingress to the fabric there, we do a lookup on, you know, the 7-tuple IP hash type parameters. You know, those parameters that we're all used to in the Ethernet world, like source and destination IP, source and destination port, that kind of thing. And we make a decision on ECMP path out of those available. The difference here is that because the VideoX switches have been constructed from the ground up, you know, as a brocaded device, and we've spun our own ASICs, we've used some of the techniques that we were using in the SAN world as well. So we're able to influence the path selection relative to the amount of bandwidth available. So in other words, we know that we've got twice as much bandwidth in kind of the left, the northbound direction, to right, the southbound direction there. So we would actually, you know, ascribe twice as many flows to the north direction as the south. So that carries on at every hop right the way across the fabric as well. So very, very good understanding of all the paths that are available, them all being open, and then very good load balancing for flows across the fabric. And bearing in mind we're going to be looking at NAS, it probably already, you know, sounds like very applicable to carrying large amounts of data across the fabric. So right now we'll look at the ISL trunking. So, you know, this is an inter-switch link, a common industry term, so just links between 2 adjacent switches in a fabric. So what, like me, you guys are probably used to only having available the 802.3 link AD link aggregation standard, you know, LACP trunking, in other words, LACP ether channel or link aggregation groups. It's known by a number of names, but the algorithm is always the same pretty much, and the techniques to load balance, again, you know, it's done by flow. So depending on how good a product is, it can look deeper into the packet header and decide how to hash it on which relevant link, but then all packets in that flow will go on one link. So you could have a situation, you know, where you've got 8 links, but because you've only got a number of flows going on, you know, you're only using like 50 gig of that available 80 gigs as we've got in the graphic at the bottom. In fact, if it's one link, that could be a massive data transfer. You know, it could be a NAS session, and that could very easily just go all over one link, even though you've got 80 gig available. Brocade ISL trunking is per packet, so frame-based round-robin load balancing. So literally, you know, you always use the entire bandwidth available. So if there's 8, 10 gig links in that ISL trunk, then we will balance the traffic, you know, proportionally across all the links available. So quite an advantage there as well. So all right, let's have a look at NAS background, then we can see how fabric applies to, you know, the technology applies to these techniques. So we're just looking to see if we've got a question, I think, at the moment. Hoping you guys can hear. We've got comments that someone doesn't have a mic, but they can hear me, so hopefully that's okay. We've had some technical problems this morning. Actually, we're running this off one PC, so we've kind of got the audience and questions over the top of the slide. So we've got a note back there. Everything's okay. So we'll just carry on. So first of all, I'm going to make this as technical as possible. We're certainly going to get it onto some technical details on iSCSI and how that's been in the product and how to configure that. So let's get onto that. But you know, a quick thing about the market here for storage. You can see it's very large indeed, and although a lot of the storage market, of course, is frame-based and it's SAN, there is a very, very large market for NAS, for NFS, for iSCSI, and you know, all the headings that would come underneath that. So it's a very, very important market to Brocade, and I think that's why we've always had capability in the VideoX products for this area, and how that will increase as well and expand. I'm going to end on some roadmap slides about future features that we're looking to enable for NAS on the Ethernet Fabric products. I thought I'd include the table of nomenclature there as well. You know, we've all been very used to gigabytes, moving on from megabytes and terabytes. So exabytes is one above petabytes, I think. So all powers of 10 increasing there. So I've lost my cursor. Let's see if I can move you on. Okay, so something else that's been happening in the industry in the NAS area is this idea of scale-up NAS versus scale-out NAS. So, you know, traditional NAS systems, you know, they had a pool of disks like we see there behind, you know, probably a pair of controls for HA. And you could, you know, scale up the amount of the storage that you have, but in terms of performance, it's difficult to add CPU memory, and the file shares are bound to those controller ports. So, you know, not hugely scaling. You could increase the amount of storage you have, but performance wouldn't really increase in linearity. We've got this move now to scale-out systems, which is really kind of, you know, a parallel computing kind of like paradigm. So we're able to just increase the whole number of NAS storage devices, and then CPU and memory will scale in a commensurate way as well. So, you know, we can present a single unified share across all the nodes. So, you know, this really means that although I'm sure, so I've lost the cursor again, but I'm sure the SAN market and block storage is still very large, like we saw, and very important to Brocade. But, you know, a lot of clients that I deal with use scale-out NAS to provide what they need for their business as well. So, problems moving the slides on. So techniques to avoid load balancing, or to enable load balancing, like we probably know, you know, NFS type NAS techniques are based on TCP, and the sessions then are bound to interface on the filer. So one of the techniques you can use here, and yeah, Isilon. So I have a lot of customers myself in the media vertical actually, and Isilon is quite a popular storage vendor for those guys, and I know that they use this DNS technique to round robin again incoming client connections across all those sort of parallel scaled out available devices. So that's something we can do as well. Something new that also arrived in NFS 4.1 is the PNFS technique, the parallel technique. So here again we're kind of abstracting really, using parallel techniques to split roles and using metadata. And even there the server is removed from the primary path. So again, another technique to scale access, you know, into this scaled out NAS type device. So a bit of background on our fabric, which you may have known already. A bit of background on NAS, which you probably knew already as well. Or let's hope that it helped if there's anything new in there. Now let's drill down and have a look at how we can actually use the brocaded Ethernet fabric for NAS devices. Right. Sorry. Come on, slide, move on. Right, so let's build this. You know, why is the... By the way, VCS, you probably know again, but that's your virtual cluster switching. It was our initial marketing name, really, for Ethernet fabric. I think we sort of coined the term Ethernet fabric, and it got picked up quite well in the industry after that. So anyway, it's a synonym, really. So when you see VCS, just read Ethernet fabric. You know, we covered already one point here is we've got very high performance, multi-pass all open, obviously highly resilient, very fast failover, and those links fail, as we'll see as well. So a very applicable architecture in that way. It's a modular approach. I haven't gone into it here, but you may well know, again, this very, very low config details. One of the other protocols that you have within DCB data center bridging, which is essentially lossless Ethernet, is the DCBX protocol, which is really based on LLDP. And this means that a lot of building the fabric is just plug and play. You need to set an bridge ID, as I said, but then you can literally just plug these devices together with standard base 10 gig or twin-ax direct connect copper type cables, and they will build the fabric and build the control plane, build the trill fabric with all paths open, like we said, without very little administration anyway, and we like to keep that to a minimum. This makes it very easy to scale as well. So you can start small and grow big, sort of pay-as-you-grow type approach. So, you know, this can match the modular approach that customers are using to NAS storage as well. You know, scale the NAS and then scale the fabric to go along with it, sort of thing. Automatic provisioning, there's a slide on this as well, but these products are very virtualization as we're aware too. We always invest a lot of R&D into new NOS releases to bringing in new capabilities for virtualization. Not only VMware actually, I mean majorly VMware, that is a very large part of the market, but we try to align any feature that we bring out so that it could be available in any other hypervisor technique like Hyper-V sort of thing. But you may well have seen already that we can administer, you know, like a vSphere login and password, and then we can pull in configuration that's already been done there into the Ethernet fabric to stop you having to define VLANs and any other parameters that you might have along the way, sort of thing. And lossless Ethernet. So this is the DCB standard, data center bridging. That's the IEEE name. There was a bit of a war of names originally in the industry here. Cisco kind of tried to define the name as data center Ethernet, DCE. Everyone else in the industry was really using CEE, Converged Enhanced Ethernet, which indeed Brocade did as well. But I think everyone decided to stop having a war there and use the IEEE name DCB, data center bridging. Not sure if it really implies what it is, but you know, again, that's a synonym for lossless Ethernet, and we're going to be looking at that in a bit of detail as well. Right, I hope I can take you through this because it's difficult for me to see the whole slide, as I say, with the cool details up in front. But I've talked about this already. You know, multi-path resilient trill fabric, all paths open. And you can see there we've got a couple of ESX hosts at the bottom, we've got NAS storage at the top. You can probably see VLAG denoted on the diagrams as well. This is virtual VAG, virtual link aggregation group. You may well be aware again already that the operating system, the CLI on these products is, you know, 99.9% Cisco-like. So this is very good where we have where customers have investment in training and understanding of Cisco CLI. It's very, very easy to migrate to these products. You know, guys could just configure them straight out of the box if they know Cisco already. The reason I'm mentioning that is I said it's minimal configuration to build a fabric. You know, any internal, the ECMP links, the ISL links, that's certainly true. Where we've got edge ports, you know, that's where there may be some configuration for uplinks to other devices. The whole cloud acts like a standards-based switch, so you know you can connect into from the outside using standards-based techniques like spanning tree if you really wanted to, or ether channel, you know, LACP links like we've got here. What VLAG is, because we've got a distributed control plane across the fabric, with no single point of intelligence, no master device, all learning of paths, of MAC addresses, of MAC movements, VM movement, vMotions indeed, because we tie a port profile to a vNIC MAC address. Once learned by any switch, that's pushed out across the fabric, so it's kind of a distributed control plane across the whole of the device. Acts like a large multi-port switch that's geographically distributed in effect. Rather like VPLS, if you know VPLS in the MPLS world, but with the added advantages of lossless Ethernet, virtualization aware, and some of the other things that we've covered. The VLAG, anyway, what happens here is that you can see we've got link aggregation groups from a single host, from a single server, and the storage at the top, into different VDX switches on the fabric. This is a distributed control plane. What we do here, we define a port channel, put all those ports into two different switches in the same port channel, and because of the distributed control plane, they understand that they're part of the same port group, and they automatically form themselves into this virtual link aggregation group. And that means then we've got very good load balancing and sharing across the link, and extremely good resilience, which I'm sure you're used to with LACP. So we've got that, and then we've got multiple trunks, so ISLs with multiple links, as we've looked at, and then multiple paths across the fabric, which are all available to ECMP. So examples of the resilience that we'd have here, IEO continues with the VLAG failure. So I don't know if you saw it, but top right went red there. So we've lost two of the links to VDX 221 there. But I mean, in that VLAG with a very good distribution with the LACP protocol, we've still got the other two links over on the right-hand side. So, a loss of some bandwidth, but I would certainly continue. And if you're not using that max bandwidth, you probably wouldn't even notice any impact at all. We've already looked at ISLs in previous slides, so I think point 2 is probably quite obvious that I/O would continue between the VDX devices when you get, single links within an ISL failing, as we saw there with that one going red. But okay, also if all the links in an ISL fail, we've actually got a path failure between those two devices. But the slide that I took you through on our ECMP path selection and hashing and load balancing again there, I think it's clear if you understand that again there'd be no impact to traffic across the fabric there. And you can see vMotion going on there, and a failure there again because of all the multiple levels of resilience that we've got with VLAGs and ISL and trill across the fabric. Again, no impact to that kind of happening as well. So auto provisioning, I talked ahead really and already mentioned some of the facilities that you'll see in the slide here. Let's just build the slide. So yeah, we can capture that configuration information from VMware, from vCenter, and then auto provision the fabric. What we have are port profiles. We normally call this AMPP, automatic port profile. So yeah, I mentioned what we did. We kind of align a port profile to a vNIC MAC address. You need to do this to maintain your layer 2 connectivity when a vMotion happens. I know other vendors kind of use soft switches running actually on the server hardware. We run everything actually within the fabric devices, and we make sure that we've got that VLAN number actually in that port profile, so that when the vMotion happens, that port profile moves with the vNIC MAC address, and then that VLAN, if it's not available at the destination port on the fabric, on the switch on the fabric, it will be automatically provisioned. By the way, though, AMPP, those profiles don't only have VLAN information, they also include other parameters like ACLs for security, QoS settings, that kind of thing. So we put a bit of thought into how that works as well. like I said, we're gonna have a look at a bit more detail on iSCSI with lossless Ethernet. So one of the other advantages was DCB lossless Ethernet. So let's have a section to actually look in a bit more detail at DCB itself and some of the standards involved. So you may well have covered this again. So, but I thought I'd at least put some information up so we all understand what we're talking about. You know, one of the standards in DCB is PFC, Priority Based Flow Control. It's the 802.3x flow control, but using that for all lanes, so the 802.1 QBB standard. Yeah, I mean, we've mentioned 802.3x flow control there. If you're industry guys, again, you probably know that's been around as a standard for many a year. It was always previously port-based, though. So where you can see we've got a single link represented here with multiple queues, like you'd be used to with you know, the 802.1q or .p priority standard, part of the same standard actually. You may have, you know, trying to use class of service with different types of traffic across each of those 8 lanes, but the flow control could only operate on the whole port. So some vendors did experiment with this in kind of back throttling a server from the switch. So if you were getting congestion, then use flow control, use the .1x to flow control the server. What happens with PFCs that's been extended to having pause frame per lane? So you can see the example of Q6 there, where a pause frame has been instigated and pause flow just for that priority lane, just, you know, essentially for that type of traffic. This was originally designed really for FCOE. A lot of the standards, a lot of the technical details for fabrics did originate from convergence within the industry, with, you know, running SAN traffic over Ethernet with the FCOE standard. We see some of that, but there hasn't been a massive uptake. So it could be that the, you know, the NAS market and the applicability of fabric products to NAS is maybe becoming more important. And as you'll see, we can use this PFC type technique for NAS traffic as well, which really gives you that bottom point on the bullet points there, doesn't it? That, you know, it allows storage traffic to get a lossless service, and we're going to have a look at how that can happen for iSCSI. Already for a number of years we've been doing that, and we're going to start apportioning that to other NAS techniques like NFS. So moving on, the other standard involved here is 802.1 QAZ, Enhanced Transmission Selection. We'll actually see this in the config on the iSCSI part. It goes hand in hand with PFC, but this allows you to apportion, you know, a percentage bandwidth for a type of traffic into that lossless transport with pause frame. So I think it, you know, starts to make absolute sense. If we think of one of those traffic types, we've got FCOE in there, but if you think of that as NAS traffic, then you know, we can guarantee we can have deterministic delivery for that NAS type traffic, possibly even with it mixed in with other types of LAN traffic or maybe other NAS sessions, as we'll see as well. So, you know, this is the idea. We can remove traditional limitations that we've had for Ethernet. And here's the example of using IP storage with this PFC type technique. So, you know, what we had here with a non-DCB switch between, you know, our server and our storage array there. It's 10 gig, there's lots of bandwidth, there's probably lots of horsepower, could well be a cut through, so super low latency, you know, nanosecond type switch, but we're still going to get unbalanced storage there. You know, it will be what we used to in the TCP world, really, typical burstiness, and if we get any kind of choke points in the network, then we're quite, you know, it's quite possible we'll drop frames and we'll need to use TCP's retransmission techniques to get over the problems in that area. When we have a DCB switch, though, like our Ethernet products, like the VideoX, I mean, you've seen how this operates now. Immediately we get a much more balanced, a nice flat line on the graph there, nice linear and high bandwidth throughput for all the streams available with NAS there. So I know that's only a PowerPoint slide, but we'll have a look at a bit more detail now about how you can actually do this for iSCSI. And, you know, and I've done this for customers myself. This is actually been in the product right from the early shipping platforms that you saw on that graphic that I put up, moving from 6720s to 8770. So as long as we've had FCOE in the product as well. So apologies if I'm not sure if the audience is entirely technical or if it's a mix, whatever. So we'll try and balance it. But I've put this slide up here because we'll see, to configure this, I'll describe it as non-obvious. So hopefully these slides will help you to actually configure lossless DCB for iSCSI if you ever have to. And this was kind of one of the missing commands. It's a key point that the default setting, you see the default. So this is the COS priority, the .1p priority. The default for iSCSI, certainly for these products anyway, is 4. And that will become, I won't say obvious, but you'll see it involved in the config, and it's kind of handy to know that that's the case. You can change it with this command, and that will mean it will be in a different position in the parameters that we see on one of the commands further on. But that's the headline from this slide, that the default priority for iSCSI is 4. By the way, what we use here to quickly describe the situation we had in the slide before, we use TLV, so type length variables, to advertise the fact via LLDP, really, in that DCB exchange for lossless Ethernet, that we have a NIC in the storage device and hopefully in the server device as well. So right across the path from initiator to target, really, for NAS, that we have DCB lossless Ethernet capability. I might as well tell you now that the examples that I'll show you are with the Dell EqualLogic storage array. The uptake has been a bit slow to actually support TLV within the adapter cards for storage devices. But I did double check because I knew that this presentation was coming up, and I haven't actually heard of new vendors making this available. So that's a bit of a drawback. But then if we've been through this, at least you know that we've had this capability for some time, and we're just waiting on storage vendors to have this TLV capability to give you lossless transport. If this doesn't happen, we're still lossless within the fabric, but the last mile link, if you like, out to the storage and again from the server may not be lossless itself. And of course the ideal situation would be to have lossless path all the way from initiator to target. So moving on here, this is from some of the documentation for NOS, for the VideoX products. What you see here is the default DCB Priority Group table. So we use PGIDs, Priority Group IDs, which are those numbers listed down the left here. Again, this is a bit non-trivial. If you haven't delved through the manuals, both the command reference and the kind of admin guide, you may start to understand the commands and think, well, wait a minute though, how do I know which is the highest priority? So you can see their high priority going up, lowest priority going down. The 15 dot PGIDs are all reserved. I've put that up straight away. They're all reserved for strict priority scheduling. So these are really, involved on the control plane, how we're distributing information across the fabric, as I've described before. What we've got down below here are PGIDs that are available for weighted round robin scheduling, and I can't see it because I've got challenges with my graph, but I know over on the right hand side on that table we've also got PFC, priority flow control, which has been talking about. As default that's not enabled, but we'll see how we actually enable that on one of the PGIDs for iSCSI. So hopefully that's some background we needed to understand that part. So now if we now move on and actually look at the VideoX configuration to support this iSCSI TLV for lossless Ethernet. These are the 3 steps really, and I've highlighted in bold those commands. This is a show run output. Obviously this is done through conft, but I've highlighted from the show run the commands which were needed to ascribe this lossless Ethernet to iSCSI. So first of all, the priority group table command. Let me annotate that for you. So the one there is the PGID from the previous slide. So I'll quickly go back. You saw down on the bottom there in the weighted round robin IDs, we've got PG1. So, you know, just one down, fairly high in priority that's available for you to configure for scheduling. It doesn't have to be one, actually. If you delve into this more and start seeing maybe documentation from people like Dell or whoever, or partners who may have done iSCSI testing, you see that you can just pick a PGID and then ascribe that to iSCSI. Another important part that you'll see in the commands here, because it will balk at you and not accept it, those numbers, you see the 40 at the top actually and the 60 that I've highlighted there, they are actually percentages. So they are traffic percentages like we saw with ETS, with enhanced traffic selection. So really what we're doing, the 2 there will really be ascribed to sort of all other traffic. We're letting that have 60% of the traffic, but PFC is off, priority flow control, so in other words it's non-lossless. So really what we're doing is using PGID01 at the top line there for iSCSI TLV with a guaranteed bandwidth, because PFC is on, of 40%. So we're guaranteeing lossless 40% of traffic for iSCSI. The other command which really allows everything to work, certainly on this first command output that I've got, show run output I've got here as well, is the priority table. This is a little bit non-obvious as well. What we've got there, you can see there are 8 numbers, 1, 2, 3, 4. So we're in position where I've highlighted there 1, 2, 3, 4, 5. But these are the cost priority IDs. So we start from 0. So we're actually in position 4 there, which is why I put up that information that position 4 is the default for iSCSI, sorry. So if you change that, you'd need to have the PGID that you've used at the top there in a different position. But anyway, hopefully you can just see how it all hangs together. We've picked an ID, we've used that ID in that position which pertains to iSCSI, and we've guaranteed it bandwidth. So hopefully that all makes sense. You can see in part 2 there that we've configured LDP, as I said. We've removed FCOE because I think that's in the default setting for VDXs, and we've instead advertised 2 parameters there, the DCBX iSCSI app TLV and the DCBX TLV as well. So this is what will instruct the NIC card, the driver, to actually advertise and then accept iSCSI TLV and interpret that type length variable, and invoke lossless Ethernet. And then the final thing, of course, is to invoke that actually on the interfaces where we have CNA, by the way, is converged network adapter, so that's an Ethernet fabric adapter. So ascribe that to the ports where we have the storage and where we have the servers, in effect. So we've got that end-to-end path, as I said. By the way, this is a useful command as well. You can see that we can use a debug command on LLDP on that port to actually interrogate and see if our configuration is correct and we are actually running iSCSI. So again, I've highlighted things that you won't see at default, or if your commands haven't quite worked. So this debug output will show you the DCBX iSCSI app and that you've configured the iSCSI app, and you can see also iSCSI app over on the right hand side as well. So that should give you a good feeling that your configs worked okay. You've also got the show CrossQ, because although it's lossless Ethernet with PFC and ETS, you can see it's closely related to the CrossQs. And again, I've made you aware that COS4 is the default for iSCSI, and if all your traffic for your sessions is being put on that queue and is using DCB lossless, then you'll want to see nice figures for transmitted bytes, transmit and receive bytes clocking up in the way that we have there. So hopefully another useful command as well. So yeah, here's some testing that was done with, as I say, the Dell EqualLogic array. Again, it's a chance for me to read my own screen, but I know at the top there, it's a simple fabric. It's only 2 switches, but of course it's more than possible to provide have congestion on that link by running, in the case at the top, multiple iSCSI sessions with large amounts of bandwidth to the two iSCSI targets, and then also to have a mixed session, which you probably may well still want to design away from, but it is really proving that you can ascribe lossless Ethernet to iSCSI traffic and just kind of best effort to other LAN type traffic. So again, there, an iSCSI session, an iSCSI target to an iSCSI target, but something like a normal FTP transfer, whatever, in non-lossless traffic over to a normal filer. And here's the kind of results that you see. So the left-hand graph is the multiple iSCSI sessions. By the way, these two graphs, read them carefully because the colors have been reversed. I don't know why. The left-hand one, we've got non-congested and congested, but the DCB, so the better traffic, is in the wine-colored burgundy there. So you can see quite an increase, even with non-congested, but like very good increase in throughput on the congested situation, which probably you'd expect. Normally things are a lot worse in a congested situation where you've got choke points in the network, but DCB is really working there to give you much better throughput. I'm challenged to read the graph again, but at least I've told you that the colors around the other way, so that again, I think that's the mixed iSCSI and TCP file session there. So again, very good throughput with DCB, which is in blue in this case. So we nearly come to an end now. Apologies if I'm running over time a little. A quick couple of points on the roadmap for NAS, because I know that we've concentrated on iSCSI because it's the feature that we have available now. So by the way, this is highlighted as non-confirmed. I did ask our product management guys if we could use this slide. I just wanted to at least provide you partner guys with some information about what we have now and what we're looking to do. Some of it's historical. You can see 2012, NAS 3, we're releasing NAS 4 now, so we're moving on from that. But, we've just been talking about lossless Ethernet and iSCSI TLV, so hopefully we're all aware that we have that available and have done for some time as well. What we see in NAS 4.1 is automated NAS prioritization. This isn't DCB actually. I have a slide on it, so let's move on to that one. But we are putting a lot of thought into the other NAS traffic types, and as far as possible making things as easy as possible to configure. So in other words, if you provide a brocaded Ethernet fabric, it will very easily provide much better levels of transport for NAS type traffic. That's the idea. So I'll explain a bit about that and what we've got on 4.1 on NAS prioritization, and a bit of a view again over on the right there. I can't see right the way to the right, I'm afraid, but other things that we're at least planning on the plan of record to bring in to NOS releases 5 and above. So NAS traffic class prioritization. So the whole idea being able to look into a packet inspection, understand what type of traffic we have there, and probably at least automatically give automatic prioritization to that type of traffic. You can see NFS TLV is there, so I don't have more information at the moment on that. That is just roadmap, but understanding how we've done iSCSI TLV, it's probably easy to at least assume how that might work with NFS TLV. So I think this is probably last slide. And this is about this kind of automated NAS prioritization. Yeah, like I've said, it is for NAS. It's for the other traffic types, and we will identify those traffic types like NFS and CIFS and that kind of thing. But really, this is across the fabric. We had an SE update ourselves recently, and I've been made aware that there will be some config, again, just on the edge ports on the fabric. It will be something like inputting the IP address actually of the storage device, and then all traffic with destination address for that device will be given this automatic NAS prioritization. After that though, across the fabric it will be completely automatic. So sorry, not the kind of drill down technical detail that I have for iSCSI. I haven't seen this in operation myself, but it is about to appear on a NOS release, so you can see this commitment to bringing out new features. So that's it really, guys. That's the end of the presentation. Just looking to see if we have questions. Sorry, we'll just see if we can drive it. So I think we see that questions are there, but the drop box, as it were, is like one line. So we're struggling to read it at the moment, guys. So bear with us. There must be a way we can expand that, I would have thought. Okay, I think I can see I can go down it line by line. Will the slide set be available for download? Yeah, I think we normally do that for all these sessions. So it's an admin thing, but yeah, you know, I'm sure it's courteous to do that, so we will. I see guys confirming that audio was okay, so that's good. Glad someone has actually heard me. Someone is asking about the FC, so fiber channel BB Draft 6. So I'm not a SAN guy actually. I'm an IP Ethernet guy. I was I've been well, I was originally a Foundry Networks guy. I was there for 6 years. I've been at Brocaded for 4 years now, so my expertise is not in that area. I am aware of those standards. I have done some fiber channel training, but I think we better take that as a question, and we'll get one of these SAN guys to answer that for you, I think. Right, just trying to read some of the other ones. Audio is okay, so that's good. Right, how much configuration work is required on the VDXs for supporting non-VMware, e.g. Hyper-V? So I said that we've, you know, developed features to make them available for Hyper-V. So, you know, encoding, the overall way we've architected has not been entirely specific for VMware, but unfortunately I haven't seen any examples of actually using Hyper-V at the moment. A lot of hype about that. I hear a lot about this appearing in NOS now, so I think that's a future, but unfortunately I don't have any details on that at the moment. So read it down again. That was the BB standard. No, so I think we're done. So I think that's all questions. So I guess that will conclude the presentation, guys. Thanks. Bye.